when the initial metacentric height is 0. Why? Because your formula of list that you've been using all this while is this: tan theta is equal to W into D upon W into GM initial. Now, if GM becomes 0, that means GM fluid initial becomes 0, will this expression be defined, or will it become infinity? It will become undefined or infinity. Am I right, guys? Yes or no?
Yes, sir.
So obviously this formula cannot be used. Then how do we calculate list? That is the last question of the sheet I have just shared with you. It came long back and long back. Okay. Now guys, we'll use the wall-sided formula again here to get the formula. I don't think the derivation they'll care, but still I'll, it's since it's simple, whatever is simple, I take you through. Whatever is little complicated, I always say just skip it unless it is part of the syllabus. Okay. Normal formula that you use for calculating list is this. In this formula, GM0 is the initial metacentric height, and of course, it's fluid. If GM is 0 as the case under discussion, the expression for calculating the list by above formula reaches infinity or is not defined. Hence, above formula cannot be used when initial metacentric height is 0. Thus, the need for discussion of this particular topic. Clear, beta? What is the issue with the formula if GM initial is 0? The use of normal formula for list also leads to increasing error in results as GM tends to 0. Now, this is nowhere written. This is my understanding of the thing, and I'll prove it through a numerical that this formula that we will get should also be used when the GM is exceptionally low. Because what happens? You are saying GM is 0, but I'm saying if G tends to 0, that means nearly 0, then what will happen? As the GM becomes smaller and smaller, this expression tan theta is tending to infinity. So if GM tends to 0, tan theta tends to infinity. So error will amplify. But formula is strictly for the case when it is 0. But the last part, if you go through the formula and use your logic, you'll find that use of this formula is also, I would strongly recommend when you find that GM is exceptionally low. Let's run through the formula first. And GM in this discussion is GM fluid. I've already said so. Guys, here is the ship which is in the upright condition with W here. Okay. Now, if you shift this W to this side, it will cause the vessel to list. And the ship has GM0. Now, she has reached this equilibrium because the righting moment and the listing moment here have become equal. Okay. Now, usually when you do the list problems, what do you take as the listing moment? You take the listing moment as small w into small d. Am I right, beta? Yes or no? Correct? Usually when we solve the questions for list, what do we take the listing moment? Small w into d in this case? Yes or no, beta?
Yes,
Am I
sir.
right? Now, in this case, I will take the listing moment in the second diagram, that is the equilibrium condition. Like we took the equilibrium condition when we were deriving the formula for heel during turning. So instead of the initial condition, I will take it from this. The two do not make a difference. Sometimes we choose the second one because by using the second one, it results into a more convenient formula. So I'll be using the writing moment and healing moment in the equilibrium condition, and I'll not take the listing moment from the upright condition. Okay. So in the listed condition, just see guys, what is the horizontal distance between the centers of gravity of the W before shifting and after shifting? You see, it goes here, this is list. Now, this is the distance in the equilibrium condition through which the weight W has been shifted. And this angle is 90. This angle is theta equal to list. Therefore, now from this triangle that has come up now, what is the horizontal distance between the two locations of W from the lower diagram? It will be d cos theta. Am I right, class? Yes or no? Correct, beta? Correct? Guys, do you agree?
Yes, sir.
So now from the equilibrium condition diagram, in equilibrium condition, that is from diagram 2, the listing moment will be small w into d cos theta. This is one expression. What is balancing the listing moment at that angle is the writing moment. Writing moment will be w into gz. Now, for small angles of inclination, you use gz is equal to gm sine theta, but here gm is 0, so you can't use it. So what do we do? For gz, we'll use the wall-sided expression. For small angles of inclination, gm is equal to gz is equal to gm sine theta. As gm 0 is 0 here, we will use the wall-sided formula for gz. And by wall-sided formula, this is the value of gz. So what do we get the writing moment as? Writing moment will be equal to W into GZ by the wall-sided formula. Correct, class? Yes or no? Am I right, guys? Now, in this, how much is GM0? GM0 is how much? This is already 0, you're saying. This is 0. Sorry, my mistake. Okay. As GM0 is 0, that means now what does it become? It becomes W into sine theta into half BM0 tan square theta. It reduces to this. GM0 is already missing. Now, guys, at angle of equilibrium, the listing moment and the writing moment are equal. So we'll equate them. We equate them. If you take the cos theta this side, sine theta upon cos theta will become another tan theta. And there is already tan square there. So it will become tan cube theta on this side. And rest everything we push onto the other side. We transpose the thing, all terms. And this will then become cube root of 2 into small w into small d upon displacement into Bm initial. Please have a good look at it. And then we are talking of this formula to be used to calculate list when the vessel's initial metacentric height is 0. You can learn the formula. It's cube root. It's not square root, class. It's cube root and not square root because it was becoming 10 cube on the other side. This formula is also in the sheet that I have sent. Only thing is there instead of D, S has been used as the distance because that I copied from the book. So that is, I just picked up from the book. So instead of D, they have used S there. It doesn't matter whether you use D or S. So would you be able to use this formula, guys, in case the question comes? You will have to substitute the values, right? Get them and substitute, correct?
Yes, sir.
What came in the exam was a straight simple one, which in which he said, I'll take that question first, which came in the exam and which has been shared with you. They were very generous to the students here because here he said clearly that the initial metacentric height is 0, 0 GM. So immediately it should strike. It came in MMD 2013, guys. It's a 2013 question. Then it was simple substitution of the values. You needed displacement. So for 8.8, you can have the displacement and you can have other things that are required. So what do you need? You need displacement, KB and KM. All these values are against 8.8. So it was a very straight, simple question that time. Now, PM will be equal to KM minus KB. You all know. Small w is how much in the question, guys? Read the question and tell me.
2 tons.
2 tons. Small d or s, whatever you want to say. How much is that?
2.45.
2 decimal 4 5. Okay. And now GM is 0. So by list formula, GM, when GM is 0, the formula we have done is this one. You can put the values and then calculate, and you'll find theta coming as 2.997 degrees. Please calculate and see that you're able to use the calculator. Please see if you're able to use the calculator.
Yes, sir, correct.
Okay. Please use your calculator. Make sure you're using cube root, not square root. For square root, you don't put 2 outside the thing, but when it's cube root, you need to put this 3 outside that symbol that you have used. So please be careful. In a hurry, don't mess it up. This was MMD 2013. I don't remember seeing it thereafter, but then you never know. Guys, if I wanted, I could have closed this topic here because there's only one MMD question where GM is 0. But I'll also take you through some my own interpretation of this, and you should be careful because tomorrow, if I have to set paper and I have to test you on this, I will not say GM is 0. I'll give you a question and say find list. And what will you do? Initially, you'll start calculating GM initial with GM fluid. And if you get GM fluid, then you'll say, okay, since the GM fluid is 0, you will use this formula. So one slight tweaking can make the difference. Maybe instead of the question saying GM is 0 as this one, you may be required to calculate. And as I said, I'll also be more comfortable using this formula if GM is exceptionally low. The moment I say this, people say, what do you mean by exceptionally low? Well, I cannot say what is exceptionally low, but as a thumb rule, I can guide you that if your GM is less than 0.005, there are two zeros. If it's less than 0.005, I strongly recommend that you put a remark and use this. I'll show you the reason for it in a while now from now. Is this question clear to everybody, guys? Can I continue further on this?
Yes, sir.
Okay. Now see here. MV hinge ship is floating at a displacement of so much in water of RD so much. This is the same question I've taken, but I've converted into this question now so that I don't have to interpolate the hydrostatic particulars again. FSM 1485, calculate the list produced if a weight of 2 tons already on board is shifted transversely through a distance of 2.45 meters. Assume the ship to be wall-sided at waterline. So I have not said GM is 0. And in such cases, what will I do? I'll get the particulars and I'll start solving, thinking it to be a normal list question. And this part we have already done a while back when we were doing the previous topic, angle of lol, guys. These values are exactly from there. So they have just been copied from there. I don't think we need to discuss them. Correct, guys? Yes or no?
Yes, sir.
Okay. What will you do? You'll start calculating the GM. How much do you get GM? 0.001. Just see, guys, KM minus KG minus FSC, right? Is it 0.001? Now it's not 0. Does it come 0.001? Can you quickly check it also?
Yes, sir. 0.001.
Yeah. PM 3.841. And now, first I'll calculate the list using the normal list formula, tan theta. I get a list of 15 point, almost 16 degrees. I get a list of almost 16 degrees. But since the GM is exceptionally low, I would prefer to use the GM0 formula. And if I put in that, what list do I get? I get a list of only 3 degrees. Guys, there is a hell lot of difference between 3 degrees and 16 degrees. Am I right? Correct? It's almost 5 times. Do you see the difference? Do you see the difference, guys?
Yes, sir.
I am saying if I reduce my GM to 0, that means I also lose 0.001 that I have. Then I'm getting a list of 3 degrees. And if my GM is more than 0, 0.001, how can my list be more than 3 degrees then? That means 15 degrees, 16 degrees, because it is tending to 0, the list is getting amplified and error is increasing because of the denominator tending to 0. Guys, I don't know how many of you would agree with it or understand it, but this is the issue out here, right? You cannot say 15 degrees because if you, my thing is, now if you make it 0.002, this and this will remain so much, this will reduce. If you make it 0.004, okay, can you make it 0.004 and find out what is the list coming then? Can you change this and calculate, please? How much does it come? Akshay, how much has it come?
4.062.
4
You
degrees.
see, the moment it has
4.06.
come to 0.4, it has come to 4 degrees, which is reasonable, right? Am I correct? Am I
Yes,
right,
sir.
class?
Correct.
Right? So that means whatever you are talking at 0.001, it is getting, because your denominator is tending to 0, the expression is causing a mathematical concern. It's a mathematical issue. Anyway, this was not in the MMD. This is my thing that you should use this formula by putting appropriate remarks, or you can calculate by both and tell him, see, I know the other one also. You can calculate by both in this if you want in the exam. No problems. It will just take another 2 minutes. And that will save you the hassles of probably, okay, this question I've already done, is it? The same question, no? Yeah, this question I've already done. Okay. Guys, with this, we come to end of this topic. If you have any questions to clarify, let me know. Any questions? Is this second topic also done, guys? Well,
Yes, sir. Clear.
okay, I'm
Yes, sir.
closing it then. I'm closing it then. Okay. Then we come to the third one. Next one. Severe weather criteria, which is if you go through your past papers, this question very often is question number 5 of your exam. Okay. Guys, this uses the concept of dynamical stability. It uses how to find the basically heel caused if there is a constant upsetting moment, which you have done in phase 1. Same thing will be used here. Anyway, I'll not start asking you what you remember, but please be careful. Now, this is severe wind and rolling criteria or weather criteria. So both will mean the same if they come in the exam. Okay. Is it related to damage stability? No. It's an intact stability criteria, beta. Okay. Now, if you see the intact stability criteria that you have done so far, you have done basically static stability, in which you did all this in phase 1. Am I right, guys? All this you did in
Yes.
phase one. It's on page 5 of your MV Hinship Stability booklet, in which there is only one change that has happened. This angle in your booklet is marked as 30 degrees, which is now changed to 25, right? This is static stability. It is in static conditions. The criteria that we are talking about is again in the intact ship, but it is for the dynamic condition in wind and weather. Okay, shall comply with the requirements of severe wind and rolling criteria. It's not a static stability requirement, but it's definitely an intact. It is not intact. It is not static intact stability requirement. But it's definitely an intact stability requirement because we are not talking of a damaged vessel. Guys, in this first and foremost, you'll have to learn to make a diagram. Some of you may have done phase one with me. In that, we said, how does the GZ curve of a upright, stable vessel look like? And I must have told you that it looks like somewhat like this. Okay, there is something you do here, but doesn't matter in this case. Is this the curve of a stable, upright vessel? Yes or no, beta? Correct?
Yes, sir.
And then in phase one, we would have said there was a question in MMD, draw the curve for both port and starboard side. So I would have said this is the curve for both the sides, but to meet the requirement of the question, in phase one, I would have said, okay, draw a mirror image on this side, right? Do you remember, guys? Some of you may have done that. Okay, if one is
Yes, sir.
port side, other is starboard side. Now, what happens in this case? This scale is positive for both red and green, and this scale is negative for both red and green. But we'll not use this diagram. What we'll do is we'll bring the other side into this is first quadrant, second quadrant, third quadrant, and fourth quadrant. We'll flip it vertically and bring it to the fourth quadrant like this. Understood, guys? So this is what you'll draw. Is that clear, beta? Am I right?
Yes, sir.
Now, in this case, for green curve, this is positive, this is negative. But for red curve, the lower one will be positive and upper one will be negative. Have you learned how to make this diagram? Have you understood making of this diagram, guys? You will not start from it, right? Is that clear, beta? Have you understood, guys?
Yes, sir.
Okay. Now we'll not call it as port and starboard. We'll call this as the lee side, leeward, and this as the windward side. Okay, in our discussion. So our discussion starts from here, this diagram. Now, this is where we start now. Okay. What is the purpose of this criteria, weather criteria or severe wind and rolling criteria? The purpose of this criteria is to demonstrate that the ship has enough stability to be able to withstand certain degree of severe weather, that the vessel can withstand certain degree of severe weather. Is that clear, beta? Any questions you want to ask on what is on display? So you'll first make this diagram, and then you'll say what does it actually wants to demonstrate. It wants to demonstrate the ability of the ship to withstand the combined effect of beam, wind, and rolling, or certain degree of severe weather. Is it clear? First slide is clear. This is the first slide, guys. The earlier ones were just to show you how to draw the diagram, correct? Clear?
Yes, sir.
Then you don't have to write all this. This is only for explanation. This is for the lee side, the other is for the wind side. You don't have to write it. Okay. Now, guys, next. On the same diagram, it continues. Okay. The ship is subjected to a steady wind pressure. That means ship is experiencing a steady wind pressure, steady, not varying, acting perpendicular to the ship's center line. That means beam wind. You're experiencing beam wind. And the beam wind will exert the wind healing moment. Every moment as a lever. So this wind causes a steady wind healing lever. So it is not, we are not talking of moment here, we're talking of lever it causes healing lever, and that healing lever will be called as LW1. Guys, a question like this we had done in question number 87 of GZ curves, if you remember, where the vessel was experiencing a steady upsetting moment of 4,500 ton meter. Does anybody remember that? In GZ curves, question number 87, the vessel
Yes, sir.
experiencing 4,500 ton meter of steady wind moment, healing moment, and heel was to be found. Then what did we do there? We first found out the healing lever. Here the healing lever is LW1. Then what did we do? We plotted the healing lever like this. Can you see this red line? We plotted the healing lever in question number 87 like this. And wherever it intersected the writing arm curve, this was the angle of heel. Am I right, guys? Yes or no? Correct? Do you remember this question 87 working, guys? If you remember, it'll be easier for you to connect. If you don't remember, then you'll have to mug it up to certain extent. Then I don't know how you want to do. Different people will have different levels now. Now, guys, it says, how do you calculate LW1? LW1 will be calculated by this formula, PAZ divided by 1000 into acceleration due to gravity and the displacement of the ship. What is P here? P is steady wind pressure, and which IMO wants you to take as 504 pascals. So P is wind pressure of 504 pascals. What is this A? Area, it is the windage area, the area on which the wind is acting. Okay, it is the windage area on which the wind is acting. What is Z? Z is the distance of the geometric center of area A from about half the draft, because that is where you expect the vessel to have the lever of this wind force acting on the vessel. So Z is the vertical distance from the center of area A to the center of underwater lateral area, or approximately half the draft. And what is delta? That is displacement. What is G? Acceleration due to gravity. Using this, so you'll have to learn this formula, PAZ upon 1000. Now, when you multiply pressure with area, it becomes force. When you multiply force with lever, it becomes moment of the force. And this 1000 and G you are dividing to basically address the issue of pascals. You're converting it into newtons and kilonewtons. And once it comes into kilonewtons, you're dividing by displacement to get it in meters. Anyway, if you don't understand this, will you be able to remember what is on display, guys? Yes or no?
Yes, sir.
Okay. I'll show it all over again. Don't worry. Now, this LW1, see what is written here. The steady wind pressure causes the wind healing lever, resulting into a heel of 50 degrees. And which side will the vessel heal? Ship will heal to the lee side. So this angle is 50. That means this wind causes the vessel to heel to 50. All clear up to this time, guys? Clear?
Yes, sir.
Yes, sir.
Now, the vessel which was at equilibrium at 50 onto the lee side is now suddenly hit by a wave. Okay, let me call it port and starboard only for the purpose of discussion. Otherwise, it is windward and leeward. In our discussion, starboard side is lee side, wind is coming from port. So now the vessel has gone to 5 degrees on the port side. Now here there is a check. Whatever you get from here, let us say I get it 5 degrees. There is a check here. IMO does not want this 50 to be more than 16 degrees or 80% of angle of deck immersion. The angle of heel under the action of steady wind should not exceed 16 degrees or 80% of angle of deck immersion, whichever is lesser. So if the vessel is heeling more than what is permitted, you are failing the compliance. You'll have to make amendments. So guys, what is the first thing? First thing is vessel is subjected to a steady wind, beam wind, causing a wind heeling lever LW1. And this wind heeling lever LW1 causes the vessel to heel through angle phi 0 to the lee side. How do you calculate LW1? LW1 is calculated by PAZ upon 1000 into G into displacement. And this angle phi 0 should not be greater than 16 degrees or 80% of angle of deck immersion, whichever is the lesser of the two. Is it clear, class? Yes or no? Clear, guys?
Yes, sir.
Yes, sir.
Okay. I am just taking it as 5 degrees. So are we complying with this requirement of 16 degrees or 80% of a deck immersion? Yes. Now, what does it say? Now, vessel which is lying heeled 5 degrees to starboard, the lee side. Now the IMO says that she is hit by a wave from starboard side. That means from the lee side. And what does the wave do? Wave will roll the vessel onto the other side. So you see the title, wind and wave rolling. Okay. So wind causes heel and wave causes the roll. So wave hits from the lee side. That means from on the starboard side. And what happens? Wave comes and hits. And what does it do? It will roll the vessel into the wind. And let us say the vessel rolls through phi 1. This is what the code of intact stability says. So guys, from the resultant angle of equilibrium phi 0, the ship is assumed to roll owing to wave action to an angle phi 1 into the wind or to the windward. That means phi 1 will be counted, measured from here like this. Suppose phi 1 is, let us say, 15 degrees. What does it mean? The ship has actually gone 10 degrees to port. Am I right, guys, in our example? Am I right? Yes or no? Correct, class?
Yes, sir.
Okay. So this is phi 1. Now, what does the IMO say further? Oh, now, how do you calculate phi 1? Now, phi 1 is calculated using some formulae and some tables in the code of intact stability. That's all you can write. I'm showing you a formula. You don't want to remember, it's okay. You can say phi 1 is calculated. Phi 1 is calculated using formulae and tables in code of intact stability. Okay. Anyway, the angle of phi 1 is calculated using this formula, and these are some constants and some tables which are used to be used in the thing. So you can avoid remembering all this. You can just replace by this statement. That is good enough. Now IMO is saying, okay, first the wind affected, it heeled you to phi 0. Then the wave has hit you and brought you to on this side, and now they're saying as the wave brought you to through phi 1, rolled you to phi 1, wave is always intermittent. Wave action is never fixed. They're saying now the wind, which was earlier causing LW1 and was steady, has now become gusty. Gusty means the wind has become stronger. If wind becomes stronger, LW, the wind heeling lever will become more. And what does IMO say? That it becomes so gusty that wind heeling lever becomes 1.5 times of LW1. So new wind heeling lever is caused because of the wind becoming suddenly picking up and becoming 1.5 times of LW1. The ship is then subjected to gust wind pressure, which results in a gust wind heeling lever of LW2. So what will happen now? I'll plot LW2 on this diagram. And how much you take LW2? You take 1.5 times of LW1. This red line is LW2. Now, guys, effectively, what has happened? The x-axis has been shifted here. If x-axis has been effectively, virtually shifted here, then what happens? Because of the the gusty wind, this will be the new angle of heel, but the vessel will not come and stop there. She will have some energy in it. Dynamical stability will represent that work done, which will try to heal her more. So, which area will represent the dynamical stability of the vessel at this time? This area, sorry, let me go on that and do it hand first. This area, guys, this is the area which represents how much energy is stored in the vessel to flip to this angle. And this area represents the energy or the dynamical stability with which the vessel will flip onto the other side. She will not come to stop here because of the momentum, she'll flip over. What will oppose the flipping? This area will oppose the flipping. So basically, you have two areas, this one and this one. One trying to heal the ship, other trying to make the resist the heel. So what does the IMO want? IMO wants that under these circumstances, what circumstances? First affected by steady wind, then impacted by a wave, and then wind becoming stronger. Under these circumstances, area B, this area, should be greater than or equal to A. Why? Because the area B should have the capability to resist the roll before the vessel gets lost or capsizes. And what up to what angle do we measure B? On top, B is bound by this writing arm curve. Down below, it is bound by LW2. Left side, it is this point. Up to which point do we go on the right to measure this area? This area on the right side is measured up to an angle phi 2. And what is phi 2? Phi 2 will be least of the three options. Least of the three options. One, angle of down flooding, theta pi, or angle of flooding, whatever you want to call it. Second, 50 degrees, guys, not 40 degrees this time, it is 50 degrees. And the third is the second intercept of the writing arm curve with the LW2. Now, writing arm curve is cutting LW2 at this place and this place. This is the first intercept. This is the second intercept. So this is phi C or second intercept phi C, whichever is the least of the three. Which three? 50 degrees, angle of flooding, and phi C. This area B will be measured up to that angle. And if area B happens to be greater than or equal to A, then the vessel is meeting the requirement. If not, the vessel is failing the requirement. Guys, I'll clear it once again and show it to you right from the beginning. And you can let me know. I'll start from here where the I'll not go to the diagram part. I'll start from here. Now, on each slide, the things are coming, and you can let me know if there is any concern on any slide which you have not understood. It is this out here. That's all. Is this slide clear to everybody?
Yes, sir.
Okay. Why I'm going in steps is you should make this diagram and then draw it in steps. Then, next slide. You don't have to write this as I told you earlier. Then comes here. The ship is subjected to steady wind pressure acting perpendicular to the ship's center line, which results in a steady wind heeling lever LW1. The formula for LW1 calculation has to be learned. It is PAZ upon 1000 upon G and displacement, where P is a wind pressure of 504 pascals, A is the windage area, Z is the distance from the centroid of the windage area to half the draft. And you'll calculate LW1. G and displacement, of course, are not an issue. Then you'll draw this LW1 on this diagram. You can see the red line coming up, which is at LW1 on the GZ scale. Now, wherever it cuts the, now, any questions on this slide, guys, before I go to the next one? Every point on this slide is clear, understood?
Yes.
Yes, sir.
Okay. Because once you learn it in steps, then this question is as good as numerical, guys. If it comes in theory, you should never leave it. It's as good as a numerical. The steady wind pressure causes the vessel to heel through angle phi 0 into the lee. Now, where will the vessel heel? Where the LW1 cuts the GZ curve. This is your phi 0. Here there is a compliance. This phi 0 shall not be greater than 16 degrees or 80% of angle of deck immersion, whichever is lesser. Is this slide clear? Clear, guys? You will not keep making new diagrams. You're loading the same diagram. Only thing is I'm loading it in steps so that you know what to draw when, and it'll be easier for you to draw it then. Is this slide now clear, beta?
Yes, sir.
Yes, sir.
Now, then the vessel is hit by a wave from the lee side. From the resultant angle of equilibrium phi 0, the ship is assumed to roll owing to wave action to an angle of roll phi 1 to windward. That means a vessel, you see from where phi 1 is marked, it's marked from phi 0 limit, and the vessel rolls this much because of the wave action. What will you write here? Phi 1 is calculated basis the formulae and tables given in Code of Intact Stability. Right, guys? You don't have to learn what follows here. Unless you are good in mugging up and you want to reproduce it, it's up to you. Clear, beta? All clear up to this part?
Yes, sir. Clear.
And now, the wind, which was all this while steady, now becomes gusty, causing a wind heeling lever LW2. And how much should you take LW2? It is always taken 1.5 times of LW1. This you must remember. And now you'll plot LW2 on the diagram. You see LW2 has come 1.5 times of LW1. So you can all draw this diagram up to this point, guys, writing whatever little we have done so far. Correct?
Yes, sir.
Write the step, load on the diagram. Write the step, load on the diagram. Write the step, load on the diagram. Or if you mug up the diagram, then that's your choice. Under these circumstances, which we have already discussed, area B. Now, which is area B? This is area B. Sorry, this is area A. My mistake. This is area A. And what this should be less than. That means area B should be greater than or equal to A, which is B. This is B. B should be greater than or equal to A or vessel to be meeting the IMO requirement. But up to which angle do we measure angle B? We measure it up to phi 2. You see, I marked phi 2. What will be phi 2? Phi 2 will be least of the three options. You can just, instead of writing this definition, rest is the definition of angle of down flooding. But you can just say it is angle of down flooding, theta f, 50 degrees, or phi c, the second intercept of LW2 with the GZ curve. And now on the diagram, I'm marking phi c. What do we mean by phi c? Now the diagram is fully loaded. Now this is the diagram which will eventually be the final diagram that you're making. Is that clear, beta? This is your complete diagram. Clear, beta?
Yes, sir.
Yes, sir.
Okay. Guys, with this, I complete the theory part of it. If anybody has any questions and wants me to go back to any particular point, and explain again, please let me know if anybody has any doubts. You see, guys, if you see it in your anyway, I'll come to that later. Now, guys, on this, a numerical has never come so far. Let me be very clear about it. But you have a question in MV Hinship, question number 123, and of course, more questions can be made on it based on GZ curve. And if you know the diagram, then you can handle it. This question has never been asked in the exam so far, but I do not rule out the possibility of this question or some other question being made and put in the numerical part. Okay, so be wary of it. I'll just take you through this question of MV Hinship. It's there with you in the solutions. You can always refer to it. It's in the book. Can you see the question, guys? Ship of length. It's not based on MV Hinship, but it is there in the MV Hinship book. A ship of length, one, I can make a question based on MV Hinship also. Okay, but this question in the book is not based on MV Hinship. Length, breadth, draft are given. Block coefficient is given. Windage area is given, including the deck cargo. The centroid of the windage area is 0.675 meters above the water line. GM fluid is given. Angle of flooding is given. During the voyage, consumption of fuel and fresh water was compensated by water ballast. That means you have taken the water ballast, so you're not allowed the displacement to change. But it has led to creation of an additional FSM without the change in the displacement or kg. Investigate whether her dynamical stability satisfies the weather criteria if a rolling angle in waves is 20 degrees. GZ values of departure are as given. Is it clear, guys? Have you understood what is there? Clear, beta?
Yes, sir.
Now, what do we have to do? First, we have to calculate LW1. What was the formula for LW1? It was PAZ upon 1000 into G into displacement. P, does anybody have to give you P? No, P is fixed. I'll show you the solution also in steps, but I'm just taking you through upfront. 504. Is a windage area given in the question, guys? Read the question and tell me. Is it given anywhere?
1600.
Yes, sir.
1600. Okay, very good. What was Z? Z was the distance of the centroid of the windage area from half the draft. So here is the water line. Draft is 10 meters. And he says the windage area is at a distance of 6 point, how much? 75. 6.75 meters above the water line. Am I right, guys? Yes or no? Correct? So what will be the value of Z here, guys?
Yes.
How much?
11.75.
11.75, right? Upon 1000 into 9.81. How can I get the displacement, guys? We have the block coefficient. Displacement will be equal to length into breadth into draft into CB. This will be the underwater volume multiplied by density of seawater. This will be the displacement. Am I right, class? Yes or no? Correct? Correct, guys?
Yes.
How much is the displacement coming? Can you quickly calculate? 150 into 24 into 10 into 0.7 into 1.025. How much is this? Sorry?
25830.
25830. So 25830 you put here and you'll be able to calculate LW in 1 in meters. Am I right, guys? You want to calculate LW1 quickly and see? How much is it coming?
0.037.
0 point
037, sir.
037 meters. Okay. We'll check in the solution. Guys, what is this 20 degrees? Okay. What will be LW2 then? It will be 1.5 times of 0.037, whatever it comes. Okay. Guys, what is this 20 degrees given here?
5.2.
It's 5.2, right? Then we need to draw the GZ curve. We need to have the corrected GZ. What has changed? Has the displacement changed? No. Has the kg changed? No. What has changed is FSM. FSC has changed. That means it has actually changed kg only, if you see, because you correct the kg with FSC. Guys, if FSM has increased, will the virtual center of gravity move up or down? If FSM has increased, additional FSM, will it increase? Will it raise the corrected kg or lower the corrected kg in GZ?
Lower, sir.
Tell me.
Lower the
Tell me,
corrected
guys.
kg.
It will? Say again.
Lower the corrected kg, sir.
Why? If FSM is increased, you are adding the correct to get the corrected kg. What were you doing? Were you adding FSC or subtracting FSC in GZ
No, sir.
curves?
kg will increase, sir.
Kg will increase by how much? Equal to new FSC caused, right? Because displacement is same. So what is the additional FSC, guys? The FSC will cause FSC created will be equal to 3410 by displacement, whatever it is, 25830, because question says displacement is same.
0.132.
So that means 0.132. That means your corrected kg will go up by this much. Am I right, guys? Correct? And in phase one, we learned that if only the g moves, then the gz is corrected by how much? It is corrected by gg1 vertical sine theta. Am I right, class? Yes or no? Correct?
Yes, sir.
Guys, yes or no?
Yes.
Yes.
And in this case, g has moved up. So gz will reduce or increase? GZ will, when G moves up with, is the GZ, does it increase or reduce? Recall that for diagram which I told you, yeah, some of you may have done phase one with me. So the guys see,
Reduce, sir.
it reduces. So that means if you apply minus GG1 sine theta, you'll get the corrected GZ, which will have to be plotted. Okay. So the guys, to handle these questions, you cannot just allow GZ concepts to go for a toss. You still have a couple of days. If you need to brush up, we have done reasonably well the phase two component. If you have some topics to be covered, please see in the past they've asked questions on dry docking, they've asked questions on GZ. So please hedge your risk by going through it. I'll show you the solution from the book itself here. Displacement, you gave me this. Additional FSC 0.132. So what is it? We correct the GG1 sine theta, and this is the corrected GZ after the additional FSM is created. Yes or no, beta? Correct?
Yes, sir.
This, I've already explained this to you, right? Because if I show you in one go, some of you will again lose context. Wind healing level, did you get this value? 0.0374?
Got it, sir.
And LW2 will be 1.5 times. This will be LW2. And now you'll draw the GZ curve with these values like this. You'll plot these values here, draw the curve, and you'll plot these values on this side and draw the curve. You'll draw the GZ curve. You see, guys, now this is from the book. These are the GZ curves drawn. This lower line is LW1. And when you plot LW1, from the graph you read that the heel caused is 4.5 degrees. This is your 50, sorry, 50. So is the vessel complying with the requirement of phi 0? It shall not be greater than 16 degrees or 80% of the angle of deck immersion. Correct, beta? Yes or no?
Yes, sir.
Yes, sir.
Then from here, the ship rolls through 22 degrees or whatever it was. And that means effectively it goes 15.5 degrees on the other side, because 15.5 plus 4.5 is 20 degrees. So this is 20 degrees of phi 2, phi 1. Now you plot LW2 and then it cuts it here, right? Now you have to calculate this area, and out of the three, 50 degrees angle of down flooding and phi C. Phi C is nearly 50 degrees. You can see here, phi C is about 50 degrees. So which one is the least? Least is 42 degrees. Yes or no, beta? Of the three, correct? So here at 42 degrees, you have drawn this, and this is the other area that you need to calculate. This will be B, this will be A. And when you calculate these areas by Simpson's rules, then you get the areas. They are calculated here. They'll come up now in the screen. You see, calculation of area A comes to 0.0398 meter radian. Area B comes to 0.0398 meter, no, 0.144 meter radians. And B is greater than A. So the vessel is in compliance. Am I right, guys? So vessel is complying with the requirements of phi 0, and vessel is meeting the requirements of B being greater than A. Have you understood better how this question has to be solved? Because when you start seeing the solution, unless it is explained to you in bits and pieces, it will suddenly you'll go for a toss. Would you be able to go through this solution at least if somebody tries to pick up the question, guys? At least that much you must has the risk, right? This question has never come so far. It is only a theory question, but I do not rule out the possibility if somebody puts it as a numerical, right, guys?
Yes, sir.
Okay. And with this, I come to end of this topic. If anybody has last minute questions before I close the presentation, please let me know. I can go back. You see how it is given in code of intact stability. It's the same stuff given there. It is presented like this. So you may have, sometimes you may struggle to decipher it, but if you go through in a systematic manner, you will have no problems whatsoever. You see, guys, this is from code of intact stability. This is the severe wind and rolling criteria, weather criteria. This is the diagram. Now, if I give you this diagram like this, then obviously you will either mug it up or you will not be able to complete. But now you know how to make this diagram, correct, beta? Is that okay? Okay. And then
Okay,
what has
sir.
he done? He's given the formulae separately elsewhere. All this is the same thing that we have covered. And you see, guys, just to okay, since I've only taken 2 pages, we don't have those tables for phi 1. I would have shown you those also otherwise. So it's the same thing that we have covered through those different steps. And yesterday we were talking of additional special criteria for passenger ships. This is what it is. This is the formula, guys. Don't get confused. Some people start sending me messages. Sir, in MV Hinship, the formula is not this. It is 0.02. This is the formula 0.2 from the code of intact stability. Okay, so please don't get confused. This is the formula directly from code of intact stability. Okay, so that takes us through this. Now, guys, this was this diagram I have shared with you in the morning, right? That
Yes.
Okay. Okay, guys, if you see my list here of the miscellaneous topics, Inclining experiment we have done. Heel during turn we have done. Then angle of LOL and GM at angle of LOL we have done. List with GM0 we have done. Severe weather criteria we have done. If you can give me another 15-20 minutes on the run, then I can do one more and the remaining will finish in the evening. Then evening I need only about an hour and a half class, right? I don't need a full class in the evening, guys. So shall I do it now or you want me to do it in the evening? Which way would you like to do? Tell me. Class?
Do it now, sir. No.
Okay. So I'll no because I'll not be able to complete the full thing in any case. So I'll do one more thing, that is rolling in still waters, and which will cover your rolling period
Sir, 5 minutes
also.
break.
Okay, take a 5 minutes break, 11:25. Okay, no problems. 11:25. Take a break. Okay. So, guys, ships rolling in calm seas of still waters and the rolling period test. Okay. So let's finish this so that in the evening we have only limited content to be addressed. Rolling period of a roll, guys. Now you see what is rolling. Transverse oscillation of the ship is referred as rolling. We all know it, guys. Period of roll is the time taken by the vessel to complete one roll, one oscillation. That means if it starts from upright, then goes to one extremity, comes to upright, goes to other extremity, and comes back. Or if it starts from one extremity, let us say port extremity, then it goes to starboard extremity and comes back to port. Each of these is case of one roll. So upright, if you start from here, then she goes to one extremity, then she goes to the other extremity, and then she comes back to upright. This is one roll. Or if you want to start from, let us say, port extremity to at the bottom, you can see she goes to this other extremity and then comes back. This also is one roll. I'm sure this we all know. There's nothing much to talk about it. Now the time taken. Now natural roll. Now guys, if a ship is stable, that means with positive GM, and she is floating in calm seas. Now obviously then she can't be rolling if she's in calm seas. So that means you have to initiate the rolling. How can you initiate the rolling? You can initiate the rolling by any of the ways. Means you can, if she is at birth, you can tighten the mooring ropes and then slacken them, and then she'll start rolling. Or you can induce any other the rolling any other way. But once you have induced the rolling, then you have to withdraw the element that induced the rolling. So you withdraw that element, and now vessel, because of momentum, will not immediately come to stop. What will happen? It will keep rolling from one side to another because of the air and water resistance. The amplitude of the roll will keep reducing, and now the vessel is rolling naturally. Why? Because it is not under the influence of any wind, not under the influence of any wave. It is not under the influence of any external factor, which is either inducing the rolling or opposing the rolling. Now the vessel is rolling purely because of her own stability criteria. And such a rolling is called as natural rolling. And the time taken to complete one such roll is called as the period of ship's natural rolling, TR. A stable ship that is with positive initial metacentric height, floating in still waters, is acted upon an external force, that is a transverse upsetting moment. She would heel over to an angle wherein the righting moment equals to the upsetting moment. So you made her incline. Now, if you withdraw the upsetting moment, the righting moment will tend to bring her back to initial equilibrium condition. However, the angular momentum that the ship gathers while returning would make the vessel roll a few times with reducing amplitude of roll before it again settles in her initial condition of equilibrium. The amplitude of the roll dampens due to air and water resistance acting on the ship. Such a roll, which roll? After the upsetting moment was withdrawn. Such a roll, which is not influenced by external factors like wind, waves, or the inducing element, such a roll is called as the natural roll of the ship. So you understand what is meant by natural rolling, guys? Is that clear? Very simple, straightforward.
Yes, sir.
Okay. Okay, anybody wants to take a slide, you can take a screenshot if you want to take anything. I don't think there's much to take on this, to be very honest, but still, anyway, it's your wish. Now, natural period of roll. Like the oscillations of a simple pendulum. In schools, we have done, what do you do to oscillate a simple pendulum? First, you take the bob on one side. So that is what you're upsetting it from the equilibrium position, and then you're releasing it. And then it starts oscillating naturally. So, like the oscillations of a simple pendulum, natural rolling oscillations of our ship are found to be simple harmonic oscillations. And this word SHM you have done in class 12. So, they are simple harmonic oscillations. Based on the simple harmonic motion concept, the expression for time period of ship's natural period of roll can be derived is this was the formula you had done in the school for the period of roll of a pendulum, where it depended on the length of the pendulum, right? Period of roll. In the ship, it is basically driven by radius of gyration and the initial K is the radius of gyration. Now, guys, it's not binding, but as a thumb rule, normal ship. Now, of course, ship shapes are getting violated because of huge container ships coming into picture. But for normal ship-shaped vessel, value of K as a thumb rule would be estimated to be about 35% of the molded breadth. This is only a thumb rule, not binding, obviously. Okay, the derivation. Ship's natural period of roll represented by TR, as you can see in the formula, is not influenced by the environment in which ship is floating, but only on the ship's inherent stability characteristics, namely the GM initial, because it was there in the denominator. It is inversely proportional to square root of GM initial. The radius of gyration about the axis of roll, it is directly proportional to K. Now, TR is not dependent. Beauty of it is TR, if you see the formula, is not dependent on the amplitude of the roll, whether the ship is rolling 5 degrees or 10 degrees. It is independent of the amplitude of roll. And GM, we all know, can be changed how? You can change the GM by loading weights, discharging weights, or shifting the weights, because the kg will change. Km may also change if displacement has changed, and FSC can change. All that can lead to change of GM. How can the radius of gyration be changed? It can also be changed the same way, by loading, discharging, or shifting of the weights with respect to axis of roll. So TR is independent of the amplitude of the roll, and GM and K both can be changed by loading, discharging, or shifting of the weights. Now we come to rolling period test, guys. Now, first and foremost, before I take you through the rolling period test, guys, we had this formula TR is equal to 2 pi K under root GGM. What is this rolling period test? Honestly, guys, it was just a simple method for the master of small ships to evaluate their stability and gauge whether it is okay or not. Why? Because you can see TR is inversely proportional to square root of GM. So if you can measure TR of your ship period of roll, then it will indirectly be indicating the GM of the vessel. Okay, and that is why it was called as the rolling period test. Now, guys, whatever we are going to talk about the rolling period test, like I told you, where all the information has been picked up for inclining experiment, likewise, where all this information that will follow for the rolling period test will come from. Guys, today the code of intact stability which is in force is which one? Which code of intact stability is in force, guys?
2008.
I told 2008. The predecessor to it was Code of Intact Stability 1993. Now, in Code of Intact Stability 1993, there was an appendix which was titled Guidance on Rolling Period Test. Guidance on Rolling Period Test. So whatever I'll be talking to you or showing will be from there. Now you'll say, sir, why are you taking it from 1993 and not 2008? In 2008 Code of Intact Stability, there is no mention of rolling period test. Now you'll say, why there is no mention of the rolling period test? As I told you, this rolling period test, the objective was to help the masters of small ships, and they suggested that 70 meters be the capping limit. They wanted the masters of small ships to use this to evaluate their stability in a simplified way. Why? Because they would have doubted the competence of those skippers to actually be able to calculate stability. So they said, okay, let's give them an easier way. But today, guys, do you need computing skills? No. Why? Because you have a calculator, you have programmed calculators, you have computers. So even the small ships are now equipped with programmed software, which can give them the stability at click of a button. You don't need to be an expert or a mathematical genius to be able to calculate the stability. My gut feeling is, my guess is that because now everybody is equipped with technology to assess the stability, probably, again, it is nowhere documented, it's my guesswork, probably that is why the rolling period test does not find its mention in the current Code of Intact Stability. Is that clear, beta? But since it continues to be in the syllabus, so I'll be using the information from Code of Intact Stability 1993. Am I clear, class? Clear, guys?
Yes,
Yes,
sir.
sir.
Okay. So tomorrow you should not think that, uh, honestly, this should go out of the syllabus in all fairness. But when will it go? Whether it will go or not, God only knows. Okay. Anyway, we'll have to study it as long as it's there. The objective of the rolling period test is determination of ship stability for ships up to 70 meters in length. Where was the 70 meters written? In the Code of Intact Stability 1993. What is the purpose? To recommend to the master of small ships a method of simplified determination of initial stability. The test may be recommended as a useful means of approximately determining the initial stability of the small ships when it is not practicable to give approved loading conditions or other stability information, or as a supplement to such information. What is the principle of rolling period test? The rolling period of a vessel depends on her GM. Therefore, if the rolling period is more, GM is less. If rolling period is less, GM is more, you know tender and stiff ships. Second is evaluation of several inclining and rolling tests established following simplified relationship between GM and TR. Now, you will say, sir, okay, they have simplified a formula, but what happens if a master has to use this formula? He still has to use the calculator. Okay, he still has to use the calculator. So what did they do? This formula was further simplified and they came to this formula. This formula base is come basis of this. So for rolling period test, because you are wanting to provide simplified process of evaluating stability, so obviously if this formula was to be used, then where is the issue? So they simplified this formula to this. In this formula, B is the bolted breadth, TR is the period of roll, and F is the rolling coefficient. F is the rolling coefficient. GM0 is the initial metacentric height. F is the factor of rolling or rolling coefficient, and B is the breadth of the ship. And TR is the period of roll in seconds. Is this clear to everybody? Everything on this slide is clear, or anybody wants to ask? This period for this test, this was simplified to this formula, right, guys? Clear, class?
Yes, sir.
The factor F, I'm sure you'll agree, in this formula, FB upon TR whole square is equal to GM initial, is of the greatest importance and is obtained based on series of tests for each ship, and that will be done by the yard or the naval architects and provided to the skipper. Factor F depends on the type of ship, its displacement and distribution of the weights, because radius of gyration and GM will depend on all these. In general, greater the distance of masses from the rolling axis. Guys, if the masses are distributed far away from the reference axis, will the this thing, what do you call it, radius of gyration be more or less? If weights are distributed far away from the reference axis or the rolling axis, will the radius of gyration be more or less?
More, sir.
More. Okay. And if radius of gyration is more than time period, the rolling coefficient will be more. So in general, greater the distance of the masses from the rolling axis, greater will be the rolling coefficient. Why? Because the radius of gyration will be more. Thus, usually, the rolling coefficient of an unloaded ship is usually higher. For the same ship, if you see its rolling coefficient in the ballast condition, it will be more than what it is in the loaded condition. Why? Because when it is in ballast condition, the ballast and the fuel is usually carried down below in the dBs. On deck, you have the derrick, crane, and equipment. So the weights are distributed away from the reference axis or rolling axis. When the ship, on the contrary, is loaded with cargo, cargo is carried in the cargo holds, and the cargo is then concentrated closer to the axis of roll. Therefore, the rolling coefficient of an unloaded ship is usually higher than that of a loaded ship. The rolling coefficient of a ship carrying greater quantity of bunkers and ballast, both groups are usually located in the double bottom, will be higher than the same ship having an empty double bottom. Now, this is just a indicative figures. The rolling coefficient of different types of ships and in different conditions are typically like this. Empty or ballast, if it is 0.88, the same ship, when it is loaded with liquid comprising of 20% load, it comes to 0.78. If you have it's loaded, then 0.75, then loaded with liquid comprising 5% of the load, 0.73, double bottom fishing boats 0.95, deep sea fishing boats, you don't have to remember these. This is just to emphasize upon the fact that F will depend on type of ship and how the weights are distributed with reference to the rolling axis. These two factors will determine the value of F. Where will the skipper of the ship get the value of F? The value of F will be provided to the skipper in different operating conditions. Okay, like in your stability booklet, you have standard 11 conditions. Likewise, he can be provided value of F for different operating conditions. Any questions, guys?
No, sir.
Now, guys, before we continue further, I'll continue rolling test later on. Then let's have these two couple of numericals. Explain how rolling period test is taken. We'll cover in a while. What is the relationship between GMT and rolling period? We just did it. Okay. What precautions must be observed when using this formula? We'll do that in a while. Now, there is a numerical. Find the still water rolling period of a ship when radius of gyration is 8 meters and metacentric height is 0.8. Which formula will be applied for solving part B, guys?
The first form.
TR
2 pi
is equal to 2 pi K
2 pi.
upon under root G GM. And then it is a simple substitution. You have to find the period of roll. So 2 into 22 by 7. Radius of gyration is 8 meters divided by square root of 9.81 into 0.8. And you can find out how much is the TR coming in seconds, guys.
17.9.
17.9 seconds is the TR. That was this question. About 18 seconds. It is August 2013. Okay. Let's take this question, guys. Now, this is directly from MMD, but my source will be examined. Now, here they mentioned 80 meters. I told you a while back, it is recommended to be used for ships up to 70 meters. But unfortunately, the question in Hinship is based on 80 meters. So it is 80 meters. But if you read the question, it gives you the rolling coefficient and it gives you the rolling period. And he gives you the breadth and he wants to estimate the initial metacentric height. So obviously, though the ship is 80 meters long, but you have no choice but to use the same formula. What was the formula? GM initial is equal to F into B upon TR whole square. Am I right, guys? Yes or no? Correct?
Yes, sir.
So it will be 0.75 is the rolling coefficient. Breadth is 8 meters and TR is 10 whole square. How many meters is the GM initial, guys?
0.36.
0.36 meters is the initial metacentric height. Yes, 0.36, correct. So guys, don't get distracted by 80 meters here. 70 meters, I told you from where the source was. This question has been copied directly from MMD, from Hinship, and there it was 80 meters. So they've continued with 80 meters here also. But let's not break our head. This is the way this question will have to be done if it is repeated. And it's a reasonably recent one, November 22. Just imagine if this question comes as a part also, even if it is 10 marks or 8 marks, I think it's worth grabbing these marks, right, guys? There's absolutely no
Yes.
reason why you should let go
Yes.
these marks or just because you have to learn the formula. Okay. Let's continue with the rolling period test. And I have told you whatever will be here will be all from Code of Intact Stability 1993, just to be able to address the theory question. Test procedure. The ship is in calm seas made to roll. Why? Because rolling period test, the rolling coefficients are given for calm sea conditions. Rolling may be induced by any method, but the methods given in the Code of Intact Stability were like this: rhythmically lifting up and putting down a weight as far off the middle line as possible. That means if the weight is picked up and lower on the sides, then it will be changing the GM of the ship, and that can induce rolling. Pulling the mast with a rope by people and running athwart ship together in unison. You may wonder, but a small boat of 25-30 meters can roll like this. Yes, so don't just, some of you may be laughing, how can it be? Now you are looking at your ship of 200, 250, 300 meters, but we are not talking of those ships. Any other means that you think appropriate which can induce rolling. As this forced rolling is commenced, because initially you are forcing the vessel to roll. As this forced rolling is commenced, the means by which it has been induced should be stopped and the ship allowed to roll freely and naturally. Clear, guys? Every point on this slide is clear? Is it clear, guys?
Yes, sir.
Yes, sir.
The timing and counting of oscillations should begin only when you judge that the ship is rolling freely and naturally, and only as much as is necessary to accurately count these oscillations. By means of stopwatch, the time should be taken for not less than 5 oscillations. Then you can get the TR by dividing the time with the number of oscillations. Allowing the roll to completely fade away, repeat the same operation at least twice more. That means 3 times you conduct, right? From the observed time, obtain the time period. The time period of natural roll thus obtained can be used to estimate the ship's initial metacentric height. I hope every point here is also self-explanatory and is clear. Correct, guys?
Yes, sir.
Now, now somebody may say, sir, then the master has to use again a calculator because you say GM is equal to FB upon TR. You're saying these people may have the competence issue. So to address that, they also used to provide something called as a diagram or a nomogram. The determination of the stability can be simplified by giving the master permissible rolling periods. That means they'll say, if your rolling period is within this to this window, then your stability is okay, depending on the draft. If draft is so much, rolling period should not be out of this limit. So this is how they could advise, or they could give a graphical representation called a nomogram, and the same the skipper could use easily. What type of nomogram are we talking about? We're talking about a nomogram like this. It has 2 scales on each of the y-axis. Here you have the rolling coefficient scale. Here you have the GM scale. Here you have the rolling period scale, and here you have the breadth scale. And then this ratio line, this blue ratio line, will be placed based on the vessel. Okay, so whether it is more to the left or more right or in between, that will be ship specific location of it. Okay, so this diagram is not universal, it will be ship specific, provided to the skipper of that particular vessel. And now let us see how this will be used with these values. You have f.8, b 9 meters, tr 12 seconds, and how do we estimate the initial metacentric height? Guys, using the rolling period coefficient scale, we mark the rolling coefficient scale here 0.8. Then using the breadth, we mark 9 meters using the breadth scale. And you see now on 9 meters you have here. We join them with a straight line. This is line 1. Now this line cuts the ratio line where? It cuts the ratio line here. It cuts the ratio line at M. Now we plot on the TR scale 12 seconds. Here is 12 seconds on the TR scale. Then join that point with M and extend it to hit on the other side. Like this. Now where this line cuts on the GM scale, you can read the estimated GM. GM is 0.36. Is that clear, beta? And this is exactly what you had read even from your calculated from your formula. Is that clear, beta? Yes or no?
Yes,
Yes,
sir.
sir.
So then the need of calculation was eliminated. Now, what are the precautions and limitations, guys? The test is recommended only for small ships up to 70 meters in length. Now you'll say, what happens with the bigger ships? Guys, as the ship gets bigger and bigger, the keel gets flatter and flatter. If you have a huge flat keel, that will dampen the rolling and will not allow the ship to roll freely. That is why it is limited only for small ships. Smaller the ship, more accurate will be the results. If your keel gets flatter and flatter, you can understand it will offer resistance to rolling and it will not allow the vessel to roll freely. Therefore, it is. So somebody may ask you why it is only for small ships. Because the bigger ships, the flatter keels will basically be a hindrance to allow for hindrance to free rolling of the vessel, natural rolling of the vessel. The ship should be normal ship-shaped vessel without bilge keel, because bilge keel. Why? What is the purpose of bilge keel, guy? Bilge keels. You all of you have seen on your ships in the dry dock. Here you have these bilge keels. What are they?
Yes, sir.
Rolling
They
over
are to
rolling कम
reduce
करने के
rolling,
लिए
right? They are to reduce rolling. Correct? So if bilge keels are there, they'll dampen the rolling and they'll not allow the vessel to roll freely. So that means the ship should not have bilge keels. The test should be conducted with ship in harbor in smooth water or minimum interference from wind and tide. Time should be observed for not less than 5 seconds of these complete oscillations. If possible, when repeating the observation of time, every time you should be taking the same number of oscillations as you took in the first attempt to establish that the readings are consistent, that is, repeating themselves within reasonable limits. I think all these precautions and limitations are very obvious, right? There's nothing highly technical about it, except if somebody says why size limit, why bilge keel should not be there, then you know. The timing and counting of oscillation should only begin when it is just that the ship is rolling freely and naturally, and only as much as necessary to accurately count these oscillations. The mooring lines, if you're doing at berth, should be slack and ship breasted off to avoid making contact during its rolling. Care should be ensured that there is sufficient UKC to allow the vessel to roll freely. It should not start touching the bottom. Weights of reasonable size like lifeboats, etc., they should be secured. If they are allowed to swing, they will affect the rolling period of the vessel. So these weights which are liable to swing should be secured. The free surface effect in the flat tank should be kept as minimum as possible during the test. Experiments have shown that results of the rolling period test method get increasingly less reliable when the GM starts reducing. And when the GM goes below 0.2 meter, then the results of this test become more and more unreliable. Why? Because when the GM becomes less, the vessel is tending to become tender. And when it is becoming tender, then you do not know when the roll starts back and forth. It will be difficult to account for starting and counting the rules. It is not generally recommended that results be obtained from oscillations taken in the seaway because the wave and winds can have their effect on the rolling period then. Therefore, we do not have the exact coefficient for tests in open waters. The rolling periods observed may not be free oscillations but forced by the wind and waves. Frequently, oscillations are either irregular or only regular for too short an interval of time to allow accurate measurement to be observed. Specialized recording equipment is necessary if you at all want to use it in the seaway. And of course, whatever you use in seaway, since the coefficient would be for calm water, the results have to be used with caution. However, sometimes it may be desirable to use the ship's period of roll as a means of approximately judging the stability at sea. If so, please be watchful. It needs to be recognized that determination of stability by means of rolling test in disturbed waters should only be regarded as very, very approximate and should not be over relied upon. So that is where we have done the precautions, the test, procedure, the principle, everything we have covered. That brings us to the end of rolling period test. And these questions we have already discussed in the course of our discussion. Correct, guys? Now, can you answer part A of this question of August 13, guys? After having done the theory now, explain how rolling period test is taken. What is the relationship between GMT and rolling period? What precautions must be observed when using this formula, correct? Clear?
Yes, sir.
Yes, sir.
Okay. So guys, with this, we come to end of this particular part. That is the rolling of the ship in still waters. And that finishes the quota for this session. Now, I'll only need about an hour to maximum an hour and a half in the evening, in which I'll touch upon synchronous and parametric rolling and deterministic and probabilistic concept of damage stability, and maybe 2 minutes of what Bongian curves are. And if you see, guys, whatever is in my miscellaneous folder, that would have been completed here, right? So there is nothing that will be left. I would be covering all that was on my list. And if you find anything which has not been covered, please do let me know in the group at any time before the exams. So I'll see if it can be addressed in the group. Is that clear, Beta?
Yes, sir.
Okay.
Yes, sir.
So we meet again at 17:30 today. Is that okay?
Yes, sir.
Thanks, yeah. Yesterday you guys showed. I was also keen to finish it off as per the schedule. So we'll be finishing the things as per schedule today. So that will give you some time for self-study. Okay. See you in the evening, guys. 17:30. Bye.
See you.
Okay, sir.
Bye.
Yes, sir.